Hey, Flip Geometry, how you doing? You ready for another one? We're going to be continuing on in Chapter 2, learning rules of logic. Today we're going to get into deductive reasoning and some of the laws and rules around deductive reasoning. And this is the mode of reasoning that you're going to use a whole bunch in this class, like from now until the class is over or Jesus comes back. And you're actually going to use this sort of logic even in future math classes. You will not be done with proofs in geometry. There's not a lot of proofs in Algebra 2, but when you get into calculus and pre-calculus, if you take statistics, if you take differential equations, it's all proofs. So make friends with it. Don't be afraid of it. It's going to become your best friend, and it's going to have lots of sleepovers with you. So make friends with deductive logic, and we're going to get right into it here. This first idea we've already covered. Inductive reasoning tends to take specific examples and extrapolate from that general principles. Oftentimes there are exceptions to the examples that are chosen, and so inductive reasoning does not always return proof. It returns evidence for something, but not necessarily proof. We would rather go the other way around. We'd rather take general principles and apply them to examples, and that does produce proofs. And that is called deductive reasoning. So rather than going from specifics to general principles and saying that these examples must demonstrate some general idea in the inductive logic, we're going to say here's general principles, and I'm going to use deductive reasoning to apply them to these specific examples and show you that this is true. Okay, so deductive reasoning is the way to go for geometry and for much of your math experience. Okay. Deductive reasoning then is the process of applying given premises to reach a specific conclusion that cannot be false when the premises are true. So we're going to have to work very carefully to make sure that our premises are accurate, and we're only going to use premises that we've either shown to be true in the past or have been demonstrated to be true, and we can take it as received wisdom, right? So deductive reasoning uses these accepted premises to show that something must absolutely be true. Just some terminology here that you're going to need. The statements that we rely on in a deductive proof, that we say because of this, then this is true. These leaned on statements are called premises, right? And the thing that you get to say at the end, I've concluded that this must be true, is the conclusion. So the premises are things that we build our argument on. The conclusion is what we produce at the end of the argument. And if the connection between the premises and the conclusion is logically correct, then we have a valid argument, okay? So you might say something like, mammals have hair, mammals nurse their young, mammals are warm-blooded, and mammals, with just a few exceptions, give live birth. A donkey is warm-blooded, has hair, gives live birth. Therefore, a donkey is a mammal. Okay, that's a deductive sort of proof. I've taken a general principle, I've applied it to a specific example, the donkey, and I have premises that attach logically to my conclusion, and so that's a valid statement, and that would be an example of a valid deductive argument. Now you can have premises that logically flow to a conclusion and have a valid argument that doesn't actually make a true statement, and that's because the premises themselves were not valid. You have to have true premises that logically flow to a valid conclusion. And if the premises are true and the argument flows and it is logically sound, then we use the word sound to mean yes, this is good. You can trust this. This is a true conclusion. Okay? True premises and a valid reasoning produce a sound conclusion. So valid means that the premises are attached to the conclusion. Sound means and those premises are true. A modus ponens. Modus ponens, also known as the Law of Detachment, is a method of deducing proofs, and it has a particular form. So there's two particular logical arguments that you're going to learn in this unit. One of them is the modus ponens, and I'll show you that in just a second here. Modus ponens relies on the if-then statement structure, the conditional statement structure. If P, then Q. And assuming that this is a sound premise, that this premise is true, then if I'm given P, then I must have Q, right? If, we did last time, if it's raining, I will wear a windbreaker. It's raining, I'm wearing a windbreaker, okay? Modus ponens is an if-then statement, and then giving you the hypothesis, you can infer the conclusion, okay? That is different from a modus tollens. And these words are a little strange, and they're Latin terms, and you can blame logicians that spoke Latin for this. But modus tollens is a method of deductive proof based on the contrapositive, and then it has a particular symbolic form. So the other one was based on the conditional. This is based on the contrapositive. Remember, contrapositive reverses and negates. So let's look at this. If P then Q, and it says, oh, not Q, then your answer is not P. If it's raining, I'm wearing a windbreaker. I'm not wearing a windbreaker. It must not be raining. Okay? So the modus tollens is based on the contrapositive rule. So, and the contrapositive, remember, have the same truth value as the initial conditional that you start with. So if P then Q, you don't have Q, you must not have P. Okay? Those are two formal kinds of logic rules that you're going to use, and you're not going to need to be friendly with. All right, congratulations, you've made it to your first two-column proof example. It's kind of like running next to a kid learning how to ride their bike, and they've always had training wheels on, and now, this moment, the training wheels have come off. Well, your training wheels are still on, but you see that they're getting a little higher, right? You're about to be doing formal two-column proofs. Let's look at this format, first of all. Here's a, on the left, these are statements. These are things that we come up with as steps towards a conclusion. Generally speaking, there are several premises here before we arrive at a conclusion. On the right side are reasons given for why we can do this, right? The first step is always given. You always write what you're told, and given is the reason. I just got that. And at the end of your two-column proof, you're going to have something that you've been trying to get to, and then the final reason. And in between, every step needs a reason. And so this is the first time you've seen this. Let's go through this slowly. They're going to give you the statements. If P, then Q. That's given to you. And they're also going to tell you, and you don't have Q, right? Not Q. That's given. You were given this by the textbook, by the problem maker, okay, by the universe. And now you can say, well, if not Q, then not P. And that's the contrapositive rule, right? If P, then Q, and not Q, oh, well, then not P. And the contrapositive rule we got last week. Now, over here, you're going to have definitions, you're going to have postulates, you're going to have theorems, you're going to have rules. And you can't have over here just because I want to, right? Over here on this side, there always has to be reasons why. So given if P, then Q, and not Q, then I can say not Q, then not P. That's the contrapositive rule. And given not P, then I can conclude not P. That's my conclusion. And that's because of modus ponens. This is the modus ponens format. If P, then Q, and not Q. Oh, then not P. Okay? We're going to do so many of these, it's going to make your head spin. The common fallacies of assuming the converse and assuming the inverse result from the misuse of modus ponens and modus tollens. Let's look at some examples of why this is true. So identify the fallacy in each argument. All dogs are mammals. Garfield is not a dog. Therefore, Garfield is not a mammal. Take a moment and look at that. Remember last lesson yesterday when we said that inverses and converses are not always true, that they often have a different truth value than the statement that's underlying it? This is an example of that. Garfield is not a dog, but all dogs are mammals. Garfield, you know, is the cartoon cat, right? Therefore, Garfield is not a mammal. Well, Garfield, the cartoon cat, is not a dog, but he is in fact a mammal. Cats are mammals too. I don't know why they exist, but they're mammals, right? Okay, dogs are way better. So all dogs are mammals. Garfield's not a dog. Garfield is not a mammal. That would look like this. If a dog, then a mammal. Not a dog. Therefore not a mammal. Well, This is not the modus tollens. This is not going back through the contrapositive. This is the inverse, right? You have not been told not the conclusion. You've been told not the hypothesis. So if they had said Garfield is not a mammal, you could have concluded that he's not a dog. But just saying not the hypothesis does not mean not the conclusion. Okay, go back and look at the difference between an inverse and a contrapositive. So this is assuming the inverse. Inverses are not always the same truth value as the conditional statement that underlies them. Okay, let's look at another one. All dogs are mammals. Garfield is a mammal. Therefore, Garfield is a dog. Well, Garfield is a mammal. He's a cat. But dogs are not the same as cats. Can I get an amen, right? Dogs, if a dog, then a mammal. A mammal. Oh, then a dog. That doesn't work because this is a converse. This is going backwards through the argument. Converses do not always have the same truth value as the statement, the conditional statement that they underlie. Okay, so be sure that you don't assume the converse or assume the inverse. The only thing that works all the time is the contrapositive. Okay, and that's why modus tollens works the way it does. Transitivity. Transitivity, or the law of a syllogism, is a method of deductive proof with a very unique following form. So transitivity says, if P then Q, and if Q then R. Therefore, if P then R. This is so much like A equals B, B equals C. Therefore, A equals C, which is the what property? The transitive property. And so the transitive in algebra carries over to logic. If P then Q, and if Q then R. So if I have P, I have Q. If I have Q, I have R. Well, then if I have P, I have R. Okay? It's just like the transitive property in algebra. Let's look at an example of that. Sorry, actually, there isn't an example of that in the slideshow. We'll do an example of that in class. We're going to look first at valid reasoning and sound premises. Does this make a true argument? So if the premises are true, I'm starting with true ideas, and I have valid reasoning, then that's the only way to get a sound argument. Okay? If my premises are true but my reasoning is invalid, they don't flow from each other, then I don't have a sound argument. I have an unsound argument. If my premises are false, then it doesn't matter if it's valid or invalid. I will not have a sound argument. I'll have an unsound argument. You're going to have to do this in class too. You're going to have to look at an argument and say, yes, the premises are true. Yes, that logically flows. Okay, this is sound. Or no, somewhere in there it broke down, and this is not a sound argument. All right, now let's look at a couple of examples. Evaluate the soundness of the following argument. Pigs are dirty animals. Is that true? Actually, I've owned a pig, and yes. Cows provide milk. Is that true? Yes. Therefore, rural areas have a low population density. What? So I've got true premises, but this doesn't have anything to do with this. Is it because there's milk and dirty animals there, people don't want to live there? This does not flow. So the premises are true, but the reasoning is not valid. So this is not sound. Okay? Here's another one. All of the animals at the San Diego Zoo are zebras. Is that true? No, I've been to the San Diego Zoo. There's way more critters there. Not true. All zebras eat marshmallows. Is that true? Well, they might have one if you gave it to them, but in the wild, not a lot of marshmallows growing in the grasslands. Therefore, all of the animals at the San Diego Zoo eat marshmallows. Now, this is valid reasoning. If this were true, and if this were true, then it would flow that zebras eat marshmallows and everything at the zoo is a zebra, so everything at the zoo eats marshmallows. That's valid, but it is not true premises, so that's not sound. Okay? So far, neither of those have been sound. Okay? So that's the kind of stuff we're going to do in class. Let me know if you have any questions tomorrow, and we'll go through them all until everybody's happy. Until then, God bless you, Jesus loves you, and so do I. Have a good night.